My name is K. Gurucharan. Today I am going to present my internship project titled Build a Real World EV and ADAS System using STM32 Cuboid and PixSim Lab on an electric vehicle. Display we have different parameters like SOC, distance, how much distance the car can travel, and range of the car, and acceleration, brake, speed, and the distance of the car, etc. In this project, we will see how all these parameters are calculated and also how others also present on the display are seen in this project. Let us consider. Tools required for this project is STM32 Cuboid, PixSim Lab, Python software, VSPE, TerraTrum. In the STM32 Cuboid, the STM32 Cuboid is a development environment. STM32 is a host where we will generate executable files. Here we use STM32F103686 microcontroller because industries also use this microcontroller. First, we do the required connections in IOC file. We will then save it, and now in main file we will write required code. After debugging the main file, we will convert it into binary file. This binary file is loaded in the PixSim lab. Now we know about PixSim lab. PixSim lab is a simulator that executes the binary file. Here PixSim lab acts like a target where we'll load binary file. Here we use Bluefield board. In PixSim lab, they contains different square parts like potentiometers, ultrasonic sensors, etc. and also a V-term. STM32 1F03686 contains Cortex series, Cortex M series. In PixSim lab, we will connect the peripherals to the microcontrollers according to the pin configuration. We will verify the output after loading the binary file using I/O terminals. I/O virtual terminals used to print outputs. The square parts we used in this project are potentiometers, ultrasonic sensors, I/O virtual terminals, and LEDs. Next, we are know about ARM. ARM stands for Advanced RISC Machine. It is ARM processor profiles are COT-A, COT-R, and COT-M. In COT-A series, A means application. It is used in mobile phones. In Cortex-R, R means real time, which is used in electric vehicles to open airbags. In Cortex-M, M means microcontroller. In this project, we will use Cortex-M profile. Again, the Cortex-M is classified into Cortex M0, M3, M4, M7. Here we will use Cort-M3. The block diagram shows the connections of the STM32 cuboid. Potentiometer, acceleration, brake, SOC. SOC stands for state of charge. Motor temperature, EV control, ADAS control, and ultrasonic sensors are little bit front and left and right. After EV parameters. In the EV part, we read the potentiometers and convert it into digital values. Here we will calculate speed, range, SOC, state of charge, torque, brake, temperature, acceleration. In the EV parameters, regenerative braking is the important one. When we apply brake, the SOC increases and speed decreases. Modes. In the EV parameters, modes are normal mode, eco mode, a power mode. In the next slide, ADAS parameters. Reading front, left, right, car distances, giving forward collision warnings, and a blind spot detection, and they use alarms as notifications, and also notifications are like false. UART is useful to transmit data from microcontroller to the other devices. In this EV dashboard, we will send it to data from STM32 to Python dashboard. In basic project to understand STM32 IDE and PiximLab. The project name is LED Blink. First project. First we will make the required connections in STM32 Cubide by opening the project. We will connect LED to pin number PC13. After saving the IOC file, we will write code in main.c file to toggle LED and also generate a binary file. And now this binary file is loaded in a PiximLab. In PiximLab, we will connect a LED to a blue pill board. We will load the binary file and see the output. And here we use all functions widely. Reading potentiometer values. Here STM32 Cubide sensor will reads the potentiometer values. The potentiometers are acceleration, brake, SOC and motor temperature to the IO terminals will display. Potentiometers. Potentiometers are devices that can vary resistance. Changing of resistance can change voltage of the device. Here the voltage range is 0 to 3.3 volts. By using potentiometers, we read acceleration, brake pedal, SOC, motor temperature. These values are analog values. In this slide, we know about ADC, analog to digital converter. In STM32 Cubide, can only read digital values. So ADC converts the analog inputs to digital values to understand better. Therefore, the measured acceleration, brake, SOC, motor temperature, etc. analog values are converted into digital values. Here in STM32, the ADC is a 12-bit ADC, 0 to 4095. The formula to calculate analog to digital converter value equal to Vin by V reference into 4095. Here the 4095 is the maximum value. To calculate Vin equal to ADC value into V reference by 4095. Here Vin equal to 0 and ADC value are equal to what? 0. Vin equal to 1.65, ADC value equal to 2047. Vin value equal to 4095, ADC value equal to 4095. From next slide, the scaling of ADC values. After reading the values from ADC, the STM32 will scale them. Means acceleration 100%, brake 100%, SOC 100%, temperature 150%. Ultrasonic sensors. The ultrasonic sensors is used to measure the distance. It contains two pins, trigger pin, echo pin. Trigger pin will be high for 10 microseconds. In the 10 microseconds, pulses are generated and they travel towards the object. The echo pin will be high when the pulses are receiving by the it will be high until all pulses are received. During echo pins is high, the time will be calculated how much time it is high. During the formula, a distance is equal to speed into time by 2. Distance is calculated with that formula. Distance equal to 0.0343 into time by 2. Here the sensors are trigger and echo. The trigger and echo pins are, trigger pin is transmitter pin which is connected to the object, and echo pin is the receiver pin which the data will receive from the object to the sensor. Timers. Timer is one major peripheral in microcontrollers. It counts time. The internal frequency of blue fill board is 72 megahertz. If we divided 72 megahertz with 72 Hz, we will get 1 megahertz. Then clock value is 1 microsecond. Timer count will increases for every 1 microsecond. In timers, we use prescaler and auto reloaded to generate interrupt at a particular time. So if interrupt occurs, then callback function will be executed. Let my PSC value is 7199, then tick values is 0.1 milliseconds will be. If I want to generate the interrupt at 10 milliseconds, then my ARR value is 99. Next slide, EV control. In this EV control, we will use calculated speed, torque, range, brake, acceleration, temperature, SOC, etc. When acceleration increases, speed increases, and torque increases, and SOC decreases. Here we understand when brakes are applied, the speed decreases and torque becomes negative. The range also vary with the modes. Some parameters are common for some same models. Vehicles like weight of vehicle, threshold values, etc. Clamp function is one of the main function we use here. Here we read the values for every 10 milliseconds by creating interrupt and print on IO virtual terminal. The interrupt is created using timer 1. Here the next slide is distance reading. Here we read the front, left, right distances by the sensors. By using 3 ultrasonic sensors, we will read the distances. We will read the distances for every 100 ms seconds. Here we will use timer 3 for generating interrupt and also timer 2 for calculating distances. The maximum distance measured by ultrasonic sensor is 400 centimeter. These distances are also printed on IO virtual terminal. By these distances, we will calculate time to collision TTC. Here the picture will understand the car with 3 sensors with the left sensor, right sensor and front sensor. The next slide is alarms. Time to collision TTC equal to distance by time. According to the time to collision, we have 2 alarms, warning alarm and a critical alarm. If TTC less than 3 seconds, we will show warning alarm T less than 50 centimeters. If TTC less than 1.5 seconds, we will show critical alarm. 2 more alarms we have advisory when speed is high and a normal alarm is. Here we also find blind spots, left blind spots and right blind spot. If sight distance is less than 30 centimeters, the blind spot LEDs will glow. We also print the alarm type on virtual terminal. Here our next slide is FSM. FSM stands for finite state mission. Here we will observe different states that vehicle is undergoing. The conditions per state also vary. The states we have are parked ready, driving, regenerative, fault. When the acceleration of the vehicle is above 2%, then the state of the vehicle changes from ready to drive state. When the brake is applied, the vehicle changes its state from driving to regenerative state. Example, brake greater than 5%. And brake is less than 5%, then the vehicle again enters into driving state. If fault occurs, then the vehicle should enter into the fault state from any state. False state. If some conditions the vehicle enters into the false state, when these conditions occurs, the vehicle should stop immediately. The false state will occur. False occurs when there is undesired condition occur. The conditions to enter into fault state are SOC less than 2%, high motor temperature or collision alarm occurs. Here we use yellow LED to show the fault. Okay, we also print the type of fault on IO virtual terminal. Shell process. When we want to verify the output of the control unit, we connect a device to see the output. Okay, here the device is IO virtual terminal, which is used to verify output. The terminal is connected to diagnostic port of control electronic control unit by using UART. But when we want to send the data to control unit, then certain process is done, which is known as shell process. Let us consider an example that I want to clear the fault. Then I will send a command fault clear to an electronic unit. This process is done in the following way. Like terminal UART to receiver interrupt to ring buffer to shell processes to process command to EV or ADAS fault. When the terminal sends data to UART, then it sends to ECU, which will create an interrupt. Then a callback function will be executed, which process the command that is sent and make ring buffer is used to store incoming commands. TerraTrum and VSPE tool. TerraTrum is used to send commands to the ECU. Generally, we use the following commands: help, speed, set, etc. Help command is used to print commands which are allowed. VSPE tool. Generally, we use cables to transfer the data, but the connections here are not done physically. So we use VSPE tool. It will connect Bluefill to dashboard. See, COM4 is give Bluefill board and COM1 to Python dashboard. Here our last slide is Python dashboard. Here the data that we are printing on IO virtual terminal is shown in pictorial form. Here there are different figures to represent different parameters. Example, speedometer, speed, etc. Here we can see SOC, EV metrics, ADAS, bird view, speed history, and alarms or speed. The dashboard color also changes according to the alarms. Required connections in the Pixim lab. The spare parts we use to read the distances and to read potentiometers, and we use also potentiometers LEDs to show alarms and faults, also shown in here. The potentiometers when the front distance is less than 200, then the critical alarm is shown and also becomes on when the left distance is less than 30. The blue LED will glow. When the left distance is less than 30, and blue LED will glow. When the right distance is less than 30, the green LED will glow. When the motor temperature is high, then also fault will be shown in yellow color. In IO virtual term will print different parameters: state of charge, torque, temperature, range, acceleration, brake for radar part, front distance, left distance, right distance, distance time to collision alarms, blind spot detections, alarms, fault seen on the Python dashboard. So okay, we will see on the Python dashboard. Here on the Python dashboard, we can see speed history, battery, and normal mode, EV metrics. Metrics have torque, acceleration, brake, motor temperature, alarm, fault, signal. Here front, right, left and right. When this similar, these changes are also shown appears on the Python dashboard. When the distance is less than 20, then we use C alarm critical on the Python dashboard. And the Python dashboard brings with the color red. And also when left distance is less than 30, the then we can see blind spot on the left. When the right distance is less than 30, we can see the blind spot. We can see the blind spot, right? Okay, can see the blind spot, right? So here, when left distance is less than 30, then we can see blind spot on the left. When the right distance is less than 30, we can see. Okay, okay, we'll see when the right distance is less than 30. Here, right distance is less than 30. We can see the blind spot at right. Here we see the blind spot is red, right. Then we can see a blind spot on left. When water temperature is high, when water temperature is high, then we can see fault, and Python dashboard also shown fault temperature is high. If we increase the acceleration, speed also increases. If we increase the acceleration, speed also increases. Here we can see speed 50. If we increase the acceleration, the speed also increases. Here the speed increases slow. In the speed history, we can see how the speed changes. Here speed changes 50 to 51. Okay. When we increase the acceleration at the same time, SOC stands for state of charge, also decreases. When we decrease